So I would like to thank the organizer who's still here, François, and also all the people who are still here after all these weeks. Okay, so I basically talk about a classical system, chain of oscillators with disorder and unharmonicity. Try to look at the question of like, do you get, what are the signatures of localization in this acting system? Okay, so this work is done with a former postdoc who was here, Manoj Kumar, who is now at Coventry. I mean, he's quite an amazing guy in doing numerics. And then David Hughes and two colleagues at ICTS who have been in this program. Okay, so the main question is we take this classical pin disordered harmonic chain. So that's an Anderson, it's known to be an Anderson heat insulator. And then if you introduce a small amount of anharmonicity in the system, it becomes, it's known that it becomes conducting. But what we would like to understand is the nature of transport in this weakly anharmonic system. So weak anharmonicity means at low temperatures. So basically try to understand transport in the low temperature regime. So this is classical, and so you can compare it with this question of MBL in quantum systems, where it is believed that there is a MBL many body localized phase, so that if you keep decreasing the interactions, at some point it becomes an insulator. Okay, so this is what you expect in quantum systems. Classical systems, you expect that there's no such. It becomes conducting for any anharmonicity. So there's no MBL phase, but you can still look for some signatures of localization. Okay, so this is the system we study, which I'll describe in more detail. And so this is the outline of the talk. So what we do is we measure the heat current in sort of a non-equilibrium framework where you attach heat baths to the system and then measure the current and so on. So I'll describe this framework. And I'll talk a little bit about usual Anderson localization in disordered harmonic chains. And some earlier work on that was done studying the effect of interactions, and then I'll describe the new results. Okay, so this is the setup that we use. Basically, it's a classical Hamiltonian with nearest neighbor interactions and maybe some on-site potential. The chain of particles, and there are n particles, and this system size is length, and you put heat baths at the two ends. Okay, so the way we model heat baths is just by so the particles in the bulk just satisfy Newton's equations, and the particles at the ends have some extra terms, a dissipation and a noise term, so that the strength of the noise is such that this corresponds to temperature T left and T right. Okay. Two different temperatures which are modeled by Langevin baths. Okay, so in this system, if you evolve it for a long time, it reaches a steady state. And in the steady state, you can compute various things. And so the kind of stuff we'll be interested in is looking at the temperature profile inside this system. And the temperature is just defined as the local kinetic energy at every site. And then you can compute what is the current everywhere. And the current is, so you just write a continuity equation for the energy density, and what you'll find is that the current is basically given by the velocity of a particle times the force that the nearest neighbor exerts on it. Okay, so just force times velocity, the rate at which energy is being transmitted in the system. So this is the heat current inside the system. And if you run this dynamics, and then you can compute this numerically. Okay, so this is something classically it's easy to do. You can study quite large system size, unlike in quantum systems where this would be quite difficult to do. Okay, so then you compute the current, and then if it's conducting, it basically means that it satisfies Fourier's law. And so for a finite system, you just measure the current, and then you can define a conductivity, which is just the current times the system size and divided by the temperature difference. Okay. So of course, if it's small systems, then this depends on the system size. But for large systems, if it's conducting, it should saturate to a constant value. Okay. Okay, so this is the setup, and then let me just talk a little bit about Anderson localization, which people typically study for electronic systems of this kind. So these are completely non-interacting electrons where you get Anderson localization. But I mean, it's an almost equivalent setup is just a chain of classical oscillators, where you could put a randomness, for example, in the every oscillator has a random frequency, and then you connect them with some harmonic springs. Okay, so this is a completely quadratic system, and this disorder is in the random springs. Okay, so now these two models are almost identical. Here the eigenstates are localized, and here what you can show is the normal modes are localized. Mathematically, they are almost equivalent. So localization just means that if it's a periodic system, you have block states like this. So while for a localized state, you have you have n normal modes, each of which looks something like this. Okay. Yeah. You can do it. I mean, you get exactly the same stuff. Okay, so I mean, if you just look at the harmonic system, a lot of it is known. So here, of course, transport is just by non-interacting phonons, and you can write kind of a Landauer formula for transport in this system. And so basically what localization means is that the transmission of phonons across this is exponentially suppressed with system size. And I mean, there are even for the non-interacting systems, there are a lot of interesting results. So if you don't put a pinning potential, then the current in the system depends on like is very sensitive to boundary conditions, and you can get all sorts of non-Fourier behavior depending on like kind of boundary conditions you put. Okay. If you put pinning at all sides, which means you have springs and so that you don't have low frequency modes, then it's all modes are strongly localized, and you get insulator, so that the current decays exponentially with system size. Okay, so now what happens when you put disorder? So this is some earlier study that we did in 2008, like 10 years back, when I mean I think MBL was still not so fashionable. But so what we basically asked is you take this Anderson insulator and then add a small anharmonicity, and what happens to the transport properties. Okay, so basically the heat conductivity. So this is the heat conductivity which we plot versus system size. So when there's no anharmonicity, it just goes down with system size. It's exponentially decreases with system size. As soon as you put a bit of anharmonicity, you find that it saturates to a finite value. Okay, so as soon as you put in any interactions, it becomes a conductor. Okay, so there's a quite dramatic transition. Out then we didn't study the low temperature behavior. So low temperature basically means weak anharmonicity. So I mean you can see anharmonicity is kind of weak, but it's I mean, so you have to really see what does weak mean. I mean, so in this case, the kind of system we studied, the localization was kind of large. So even though lambda equal to 0.004 is not really that weak. Okay, so and we found that the temperature goes down as some T to the power half at the lowest temperatures we studied. Okay, so now another model that was studied later was a slightly different model, where you put the anharmonicity not on like on site but on the springs. Okay, so here if you switch off the anharmonicity, you can see that these are just isolated springs, which are completely obviously it's the strongest localized system. Okay, so this model is called FSW model. I think Froelich, Spencer, and Wine. And they had some rigorous results on this model at 0 temperature. So what's good about this model is that the localization length is extremely basically 1 when there's no anharmonicity. So the effect of disorder is really strong. So it's easier to study the effect of like whether if you want to see a transition. Okay, so in this paper, what they studied is this again the conductivity versus temperature, and so this is one of the interesting questions, like how does the temperature conductivity decrease? I mean, so we know that as T goes to 0, it has to vanish the temperature, but what is the dependence? Okay, so here they found a stronger temperature dependence as T to the power 4 at the lowest temperatures they could go to, and so here, of course, I mean, as you go to lower temperature, the heat, I mean, the conductivity is so small that it becomes difficult to thermalize the system. So you can go to like not too big systems, even in this classical. Okay, I mean, here the authors did have an analytical argument, but I'll discuss the analytical argument later. Okay, and then there's another sort of set of work on classical systems is this work of Arijit Pal and all. So where they took a set of spins, classical spins, and with a random on-site magnetic field. And basically they again looked at diffusivity, but using not a non-equilibrium setup, but using Green-Kubo. And then again, they asked this question, like, how does it decrease with interactions? Like, how does the conductivity change with interactions? And here they found a power to the power 8. Okay, so it seems like as you, so there's a strong indication that there's a very high, very slow growth at low temperatures. So this would correspond to T to the power 8 dependence on temperature. Okay, so then there's been some theoretical ideas due to David Hughes and Basco and François. And so basically the idea is that in the absence of interactions, so if you don't have any interactions, then basically how does transport takes place? It's because, I mean, so all the states are localized and they don't talk to each other. And then you have some localized states which connects well to the two reservoirs. And then of course you expect that since it's exponentially connected to the reservoirs, the heat current should decay like that, right? So this is for a this is so therefore you expect that if there are no interactions, the current should go decay like that. So now as one switches on interaction, what do you expect is, okay, so now this is like an integrable system in some sense, right? It is an integrable system with localized centers at every point. Now when you switch on interactions, the sort of physical idea is that you develop some chaotic islands of which are formed by few particles which are in resonance, which I'll explain in bit details later. But this kind of chaotic islands act like local heat baths. Okay, and then I mean, you can argue that this local heat baths in this long chain are kind of separated by some typical distance. And then between this local heat baths, you have some localized state which will transfer energy. Okay, but these chaotic islands, of course, do not. The distance doesn't depend on system size, so therefore you get diffusive heat transport through this mechanism. I hope this is kind of clear, but I'll repeat this again later. Okay, so therefore you expect that from this argument that so basic idea is like, okay, so you have this long chain and these are the heat baths, but now you develop this local heat baths somewhere, and the typical distance between them is some L C, that's what I call. And then of course there are still localized states out here, and then so energy kind of hops between these islands. Okay, so that's the rough picture. And so therefore now you get system size independent current, and you get a sort of highly, so it's you kind of get an Arrhenius kind of temperature dependence of the conductivity. Right, okay, so now I mean then there are some rigorous results from François, which says that which basically proves that the conductivity should decrease faster than any power of temperature. So this is some rigorous work. Okay, so so this of course then motivates us to really try to understand this temperature dependence more systematically. Okay, so this is again the same model. So we again went back to this model and tried to do numerics for this. Okay, and okay, so let me again say that this is the disorder. So the every spring out here is a random variable, and then the coupling is this fourth order term. Okay, so without the coupling, it's obviously insulator. There's no transport, and we want to see what is the effect of this coupling. Okay, and so this is again the setup. We just do this non-equilibrium simulations with heat baths and measure the current and compute the conductivity. And we do so when you you do this for a given realization, and of course then you have to average over various disorder realizations. Okay, so one thing that you can quickly check in this system is that there's some simple scaling arguments which show that the conductivity depends. So there's this. So this is the. So what are the parameters? So this is the anharmonicity strength nu. There's temperature and then system size. Okay, so you can what you can show is that the conductivity just depends on the combination nu times temperature. So you can fix nu to be 1 and then just vary temperature. Okay, and so now I'll just show you the results. So what we do is we take systems of various size, compute the conductivity, and then we want to see what happens when you increase system size. So it should saturate to a constant value. If it's insulated, then of course it should decay to 0, right? Okay, so this is at 3 different temperatures. I show data for different disorder strengths. So what is interesting is that, so this is conductivity versus system size. And if this is strong disorder and this is weak disorder, okay. So the main message here is that for weak disorder, you see that the conductivity kind of increases with system size and saturates to a finite value. While for strong disorder, it first decreases and then saturates to a finite value. Okay, so there's these 2 different approaches to the. So eventually, it always goes to a finite value because it's always conducting. Okay, and then so these points are the data like from numerics, and then the solid fits are some sort of specific forms that we have, which I'll explain. Okay, so of course, if you go to high temperature, then you don't see this kind of transition in behavior. Then it just looks like weak disorder case. Okay, I mean, so what this means is that at some particular disorder, it's quite interesting that the conductivity is almost flat. Okay, there's almost no dependence on system size. Okay, and this we can see here also. Basically, it shows that if you plot conductivity versus the disorder strength, then at some disorder, I mean, it's all system sizes have the same value. Okay, so now can we understand these 2 different ways that the conductivity approaches the asymptotic form? So there's some simple finite size scaling analysis that we suggest, which is basically that in the weak disorder limit, I mean, it basically looks like, so if you have supposing you have the pure system, then of course, if you look at small systems, the main scattering comes from boundary effects. And then if you go to large system size, then somehow the boundary effect becomes less important, and then you get a finite conductivity. So you can try to fit it the resistance comes from sum of the boundary and the bulk, and that's so it's a sum of 2 terms, and this would explain this kind of the data that we see. Right. On the other hand, for strong disorder, I mean, there are kind of 2 parallel modes of transport. Of course, at very low temperatures, we don't have this chaotic islands, and then basically there is this localized mode which carries energy. And then at sort of the other parallel mode of transport is through these chaotic islands, okay, and then they just add up, okay. So this, if you use this form, then this explains why the conductivity, this kind of decay that you see, okay, so right. So now I'll try to from using these forms, I mean, we can fit the data that I showed you here, and we can extract the asymptotic kappa infinity. Okay, so that's the infinite limit thermal conductivity, and then we want to understand how does this infinite limit thermal conductivity depend on temperature, right? Okay, so one interesting thing is just this finite size effects, and then we try to now understand the form of the infinite limit thermal conductivity. Okay, so this is what kappa versus temperature look like. Okay, so this plot out here, this is for the pure case. Okay, if you didn't have a disorder, then the thermal conductivity goes to 0 as just linearly with temperature. And if you put in disorder, then it's this curve. Okay, and what you see here is okay. So there's like if you look at some temperature like this, you get T to the power 3.3 and then T to the power 4. So this is so the I mean, the earlier simulation result was had stopped at some temperature like this, and then you get T to the power 4. You go down lower, you see T to the power 8, and then of course it becomes really hard to go down further. But it's clear that yeah, it agrees with the predictions that the temperature is faster than any power of any polynomial. Okay, and then what we, of course, here you have to keep changing the power, but now can you try to fit the whole thing to one form? And so what here I show is like this is data over a large range of parameters with different T and delta. And what we find is that the conductivity has this sort of nice scaling form. I mean, it depends just on delta by T. Delta is the disorder strength, T is the nonlinearity. So it scales with delta by T. So all the different data for different T and delta collapse on one curve. And so the collapse is not so well when the disorder is weak, which is also expected. But for strong disorder, the collapse is kind of good. And then so if you look at here, these are systems which are finite size systems, okay, and it's still not converged to the asymptotic form. So this is 32 and this is 64, but we expect that you can see it's going down, right? So it's plausible that it fits to this line even at very low temperatures. Okay, so what is this form? So it's this exponential of minus delta by T. So it's an Arrhenius form with correction which looks like that. Okay, so yeah, so now the question is where does this come from? Okay, can we understand this Arrhenius form? And so this is the basic idea, which is again from this idea of chaotic islands. And okay, so what we find is that this chaotic islands can be found by this oscillators in resonance. So if you have any two oscillators whose frequencies are kind of less than temperature, that's what is called a resonance. And then you find that you can generate chaos in the system. So, I mean, there's a paper in 2012 by Basco where he argues that actually you need 3 oscillators, but we find that 2 oscillators are sufficient. Okay, so now if one oscillator, just a single resonance in the system is sufficient to generate chaos, sort of chaotic island, then so what is the probability of generating these chaotic islands? That's just T over delta, because delta omega is the range of frequency and the full range of frequencies is delta, right? So that's the probability of forming such a island anywhere. And then the typical distance between this island should be 1 over T, which is delta over T. And then it's basically this picture. This distance is delta over T, and then you have a localized state which transmits energy between the states. And so you get a current which scales like that. And so that's how this Arrhenius factor comes. So notice that if you needed 3 oscillators in resonance, this would be T over delta square, which would give a much faster decay than what we see. Okay, so okay, so there's of course this localization length, and this one can kind of argue that this should have also a logarithmic dependence on temperature. That of course is kind of difficult to see in the numerics. Okay, so I just want to show some evidence that 2 oscillators are actually sufficient to get chaos, and you don't need like 3 particle resonance. Okay, so this is a simulation where you just take 3 oscillators with this nonlinear coupling, and then you tune the frequencies such that either maybe delta omega between one pair is kind of small compared to the temperature, and the other one is kind of off resonance. Okay, So the earlier prediction was that you need all three to be tuned to get chaos. And what we show here, okay, so supposing you look at the red curve here, so this corresponds to okay, so set 1 is like 2 oscillators very close in frequencies, and the third oscillator is completely off resonance, right? So that's set 1. And if the temperature is kind of large, then you get this kind of a finite Lyapunov exponent. But if the temperature is let's say small, then it just goes down. Okay, so you definitely need the resonance to get chaos. But this is with 2 oscillators, so that's sufficient. Okay. On the other hand, so you need 3 oscillators, but you don't need. I mean, you don't need all of them in resonance. I mean, you just need a pair in resonance. So if you take just 2 oscillators in resonance, that's also not sufficient. Okay, so this example where you just take 2 oscillators, which still satisfy the resonance condition, but again you find that the Lyapunov exponent just vanishes. Okay, so you need 3 oscillators, but only 2 in resonance. That's sufficient to generate chaos. That's what this numerics suggests. Okay, so the other thing that we studied is, so far I talked about the conductivity. Then another sort of interesting thing in sort of localized systems is the temperature profile. And what we find is in the Wick, Wick disorder limit, you get profiles which, as you increase system size, they go to some sort of linear profile, and then as you increase disorder, you get a profile which is actually explained by this. So this is at a temperature where the conductivity is depends on T to the power 0.33, right? So then, if you just use Fourier's law, you can explain this profile completely using this law. Now, if you go to really strong disorder and low temperature, then what we find is sort of step profiles, which you expect in many body like MBL systems. Okay, so this is this is also an indication that it's kind of strongly localized. Okay. So I just want to point to an earlier study with where we looked at such step profiles in MBL systems, both quantum and classical. And you clearly see these step profiles. Okay, so this is in a XXZ chain with Lindblad driving, and as you go to the MBL phase, you see this clear step profiles. Okay, so in this, what I showed here is that you see similar profiles out here. The other thing we studied is, I mean, there are some ideas that if you look at in quantum systems, if you are in the, I think in the MBL phase, then this sort of OTOC is grows, has a logarithmic growth instead of ballistic growth. And we check this in our system. So here I mean, this is the object that one studies in quantum systems. So instead of correlator, I use the commutator. And the classical version of this is just the Poisson bracket square, which just corresponds to putting a perturbation at the origin and looking at the response at some distance x. Okay. So if you look at this object, then you see this completely ballistic growth. The only difference between the strong disorder, weak disorder and strong disorder is that the velocity is kind of smaller and the Lyapunov exponent is smaller. But you don't see this logarithmic growth. So I just want to say we also looked at correlation functions. So this is equilibrium correlation functions for, let's say, energy. And here what you see is that we at all disorder strengths, we see diffusive behavior, but sometimes it's highly non-Gaussian. This we don't understand. I mean, so one idea is that where you could get non-Gaussian but diffusive peaks is that if you have kind of random diffusion constants at different regions in space, right? Which is probably consistent with the idea of this chaotic islands. But we expect that maybe this should become Gaussian at large times. Okay, so some questions that remain are that, I mean, how do we really establish this proposed mechanism of transport through this chaotic islands and true temperature dependence? Okay, so one alternative mechanism that that I learned from François during this conference is that maybe these chaotic islands are not really fixed, but they move around. Okay, so it seems you don't need to, in that case, you don't really need this fine tuning of these resonances. And this is, so for the discrete nonlinear Schrodinger equation, there are some quite sort of rigorous arguments due to Vasco, which suggest that you don't really need these fine-tuned resonances, but if you have, you can just generate chaos out of like long enough systems which are yeah, somehow close to resonances. Okay, so once you take a big enough system, it can automatically generate the required resonances. Okay, and this suggests that the conductivity should be, instead of Arrhenius, it should be like log of delta by 2t cube, which is of course very hard to differentiate from Arrhenius from in with our existing data. And of course, we are trying to look for, I mean, if there's some way to differentiate this. So one maybe result that I'll quickly show is that, so if there are these chaotic islands, so I just showed this results for the temperature profile, where if you put a high temperature here and a low temperature here and you have a localized system, then typically you get some temperature profile like that. Right now, so now of course, if there's a sort of chaotic island somewhere in the middle, then that also acts like a thermal reservoir, and then what you expect is that maybe you should get profile like that. Okay, so that's one direct way to check if these chaotic islands are real or not, and this is something we tried. Okay, so this is so these are 3 different samples of a system of size 32, where we try to, here I just show the disorder realization, and here I show the temperature profile. Okay, so so the question is, like, if you put a resonance by hand at some point, do you get this kind of 3-step structure? Okay, so this is something we, so here right now, if you don't put the resonances and not put the resonance, you can't really differentiate. So it's not completely clear that this shows anything. Okay, so I think it's gone. So, but I think I'm just in time. So basically, we looked for signatures of many-body local in a disordered atomic chain to study of this non-equilibrium steady state. And so one interesting thing is this sort of crossover between the between strong disorder and low disorder regimes with different finite size scaling behavior. And then we showed evidence for this kind of dependence of the conductivity. And then we looked at, discussed these temperature profiles, which are sort of interesting in these many-body systems and localized systems. And then one interesting result is that what we show is that these resonant pairs are sufficient to generate chaos. You don't need a triplet resonant pair. And the interesting question, of course, is that maybe you don't even need this resonant pair, and you can still get, there's a weaker condition to generate chaos in the system. And then we looked at this object, and there's no system right now, there's no evidence of it. And this is the reference.
Thank you. If the transport through these systems would really only be due to these quenched resonant spots, would you then not expect actually to see subdiffusion?
It's not through the resonance spots.
So if the transport is as your first theory, right?
Yeah.
So only due to the resonances that are basically fixed in space.
Right, yeah.
Then I think that you would just expect subdiffusive transport rather than diffusive transport.
No, why?
right? Because then you can, so these resonances occur at random places, right? So you will have stretches of long resonance-free stuff, which would, and the normal argument for subdiffusion would, I mean, do I make sense?
Okay, yeah, that's what, like in your model.
Actually, I guess the real question here is how strong is the evidence that it's actually diffusive and not subdiffusive? I think that's my real.
So for a subdiffusive system, I mean, if you do the non-equilibrium thing, what do you expect? I mean, does it have a, so the conductivity goes to 0, right? That's what you're saying. Even at finite temperature. So you're saying, but yeah, that's, I mean, at least we don't see it definitely, right? I mean, what you're saying is that the conductivity should actually go to 0 at a finite temperature. Yeah, this we definitely don't. Yeah, it looks. I mean, it's not always. Sometimes it's like with some powers, like a stressed exponential. I think it's like there are some toy models where you have a system like just diffusing particles, but in space the diffusion constant is like the diffusion constant is not constant, but is chosen from a distribution, and then you can get such a non-Gaussian profile.
Argument about resonances or for
Okay, quantum systems, I don't know. I mean, there should be some similar argument, which is right now, I think it's not developed.
So you said fuzzy periodicity model.
Yeah.
Very similar, but one.
Yeah, but I don't think anyone has studied with interactions. So that's of course. Without interactions, you get the same, exactly the same kind of. You get this.
Analog of single particle.
Yeah, you can even okay. I mean, at least you'll get the bands and all that. Now, of course, I don't know what it means to have, like, you don't have, of course, you don't add fermions. So there'll be a bit different final behavior in conductivity and all, because the statistics is different, right? But the single particle spectrum and all is identical.
Okay,
In what do you mean? Tropy, of course, no. I mean that it's equilibrium. Okay, that's an equilibrium thing, right? I don't know where it shows up here.
any further question? Okay, so I would like to thank you all for coming here and for many nice talks, many nice pedagogical lectures. And then I would like also, I think Abhishek should deserve some special applause, right? I mean, there were many organizers to this conference, but I think it's fair to say that the work was not really equally shared. And in particular, Abhishek really did a lot to bring us here. So thank you very much, Abhishek.